let's talk about the strategy for using energy conservation or the work energy theorem. And I will run through an example of doing it. You will find that the strategy is very similar for using the work kinetic energy theorem. We are going to define systems and we are going to define states in order to solve the problem. The first thing you should do is define your system so that way all the conservative forces and dissipative forces are internal to the system, and leave all the non-conservative forces to be external forces. Or if you want, you can include the non-conservative forces inside your system, so long as those forces do zero net work. Once you have defined your system, you are able to determine whether energy is conserved or not for that system. So go check that next, see if there is no net work done by the external forces, the non-conservative external forces. According to the strategy that we have made, the external forces are non-conservative. Choose two states of interest for the system, a state A and a state B, an initial state and a final state. So for an example, these states could be 2 points in time of an object's motion. So an object might be rolling downhill, and maybe the initial state will be the object at the top of the hill, and the final state will be the object at the bottom of the hill. You can choose any two states that you wish for the system, so long as energy continues to be conserved if it is, or you are able to calculate the work done if you're using the work energy theorem to solve the problem. But you can choose any two states that you wish, so choose them conveniently and in accordance with the information that you have been given in the problem and the information you are trying to find. You will notice that aside from step 2, setting up the problem to solve by conservation of energy or the work energy theorem is all the same steps. We're going to calculate the kinetic energy and potential energy at both the initial and the final states. So using our example again, maybe you have the top of the hill and bottom of hill for the object's motion. You calculate the kinetic energy at the top of the hill and the kinetic energy at the bottom of the hill. You'll calculate the potential energy at the top of the hill and at the bottom of the hill. Then also, if there is friction as the object changes its state from its initial to final state, as it moves from the initial to final state, include a thermal or internal energy, as it's sometimes called, term as well. Calculate what that should be. Or if you're using the work energy theorem, calculate the work done by that dissipative force, by friction. Once you have done that, calculate the work done by any external forces as the object goes from the initial to the final state. So maybe you have a pushing force, or maybe you kept friction as an external force. You didn't bring it inside your system, and so it's an external force. Then you calculate the work done by friction or the work done by these other external forces as the object goes from the initial to final state. So in our example, as the object moves from the top of the hill to the bottom of the hill. This is a step you only need to do if energy is not conserved, because the way we define our system, only external forces will have a work term to them. So you'll calculate the work done by external forces only in the case when energy is not conserved. Because if energy is conserved, there is no net work done by external forces. Finally, once you have calculated all the terms for your equation, whether you're using energy conservation or the work energy theorem, place all the quantities into the equation, and then solve for whatever you are looking for. So that's the strategy. Let's give an example. Let's suppose we have an object sliding downhill, so sliding down an incline, and there's also friction on the incline, so it's an incline with friction. Let's solve the problem for what is the speed of the object at the bottom of the incline, given that it starts from rest. All right then. So how can we solve this problem? Well, let's go through the steps. Let's define a system so we can solve this by energy conservation. So I'm going to need to create a system so that way I have everything internal to the system except for external non-conservative forces that are also not dissipative forces, so not friction forces, for example. All right, so if I'm going to do that, then I'm going to need the block, I'm going to need the earth, and I'm going to need the incline so I can include the force of friction inside my system. So that's my system, block, earth, incline. And that's my attempt to draw a box around it so you can see everything that's inside the system. All right, then next we need to choose two states for the motion. Let's choose state A to be the block at the top of the incline when it starts from rest. And we'll choose state B to be when the block is at the bottom of the incline. Why did I choose that? Well, we want state B to be when the block is at the bottom of the incline because we are looking for its velocity at the bottom of the incline. Therefore, we want to include that velocity in our equation, which means we want to have information about our block at that state. We want our state to be when the block is at the bottom of the incline so we can have information about the block at that position. And then why did I choose state A to be when the block first starts falling? It's because that's where we have some information about the block given to us. We know that its initial velocity is 0. Then d equals 3 meters is how far it slides down. That's also a given part of the problem. So we know there's 3 meters from state A to state B. And the height, well, the way I drew it might be a little unclear, but I intend that to be the height of our block in its initial state, its initial height. So that's why I chose state A. That's where we have information about our block. And that's why I chose state B, because that's where we want to find out information about our block. So now that I have that, what do we have for kinetic energy? Well, kinetic energy in state A, our initial kinetic energy, because that's the initial state as well, is 0. All right. How about gravitational potential energy? Well, if I make h equals 0 be at the bottom of the incline, as we often do, then the initial gravitational potential energy will be mg h initial. Do we have anything else? Nope, that's all we have for state A. All right, what about state B? Well, in state B, our block has kinetic energy, and it's going to be 1/2 mv final squared, because v final, ke final, the final state corresponds to state B. What about gravitational potential energy at the bottom? We have 0, because we have 0 height at the final state at state B. All right, so I've calculated all the kinetic energy and potential energy terms. I've also got friction, though. So because I have friction, I need to do the next step of the strategy and calculate the work done by friction as it goes from state A to state B. Or, since I'm using energy conservation, I just need to calculate the change in thermal energy as we go from state A to state B. Well, we know how to do that. Change in thermal energy, or sometimes called internal energy, is mu k. And then it's going to be the normal force of our block. So we need some information about this angle here. I'll just make it 30 degrees. And then in that case, as you know from doing this sort of problem in other scenarios, we're going to get mg cosine theta for the normal force of the block. And then we need to multiply the distance that the block slides from state A to state B, and that's a distance d. All right, putting it all together then, energy conservation says 0 equals change in kinetic energy plus change in potential energy, and then plus change in thermal energy because of how we define our system. We then plug in the various quantities. We have 1/2 mv final squared minus 0. Our final potential energy is 0. Our initial potential energy is mg hi. And then we have our change in thermal energy. And there you have it. So now we can plug in all the values that we know and solve for v final. Before I do that, I just want to show you another way that you can do this, which I like to do. Firstly, remember this is the kinetic energy for all the objects in your system and all the potential energy of all the objects in your system. Don't forget that. We only have one object, so we only have one term. If we had multiple objects, though, in our system, multiple blocks, then you would need to write the kinetic energy change for all of your blocks and the change of potential energy for all of your blocks and the change in thermal energy due to each of your blocks sliding. So each of your blocks sliding gets one of these terms. But anyway, one thing I like to do is I just jump from this equation down to the following. Because the mass doesn't change, I can write my kinetic energy as follows. And then similarly for the potential energy, then I just write whatever my thermal energy should be. I then consider what each of these quantities should be. I know the initial speed is 0, so I cancel that out. I know my final height is 0, so I cancel that out. And then I simplify the equation down, and there we have it, which is the exact same as what you would get if you simplified the earlier expression that we had up here, because they're the same expression. So either way, whether you do it this way or this way, you end up with this. In the future, I will always be doing it this way because it's a little bit quicker. All right, so now I have I've simplified my energy conservation equation, and I have as follows, and I can solve for final velocity. So firstly, you will notice, because of how I've written things, the masses all cancel. I can divide by mass on all sides of the equation. Then I can move this term and this term over to the left-hand side of the equation so I can solve for final velocity. And final velocity will be as follows. And there we have it. We have solved for final velocity. If you really want to plug numbers in, we can do that as well. And then we can plug that into our calculator to get a numerical answer. And I get about 5.84, which, since everything was in SI units, this is in SI units too, meters per second. All right, but now let's change the problem just a little bit. So we're forced to use the work energy theorem. What if instead we also had a pushing force on our object? So let's say we had somebody who is also pushing our block downward. What happens then? Well, since I don't know anything about this pushing force except that it's a constant force, because that's what I'm going to make it be, and we'll just say that it's like 2 Newton. Since I know nothing else about this force, I can't really write an energy term for it. So I'm going to be forced to think in terms of the generalized work energy theorem. But I can keep everything else the same as I want. Or if I wanted, I could move all these over to the left-hand side and I could calculate work terms for them as well, as I explained in another video. But I'm going to keep everything the same. I'm just now going to have an additional work term here. All right, well, that being the case, how does this change? Well, instead of having 0 here, I now have the work done by my pushing force, which is going to be Fp times the distance, because the pushing force is parallel to the ramp. So the distance is just d, the force is just F, and it's a constant force. So I can use this formula for calculating the work done. The force goes in the same direction as displacement, so positive work is done. Means the rest of this, we have this extra term in our equation. So now when I go to solve for final velocity, I'm going to have this extra FPD term, which algebraically you can confirm turns this into, we now have this plus 2FPD term. So now we have this as our final velocity. And then over here, we have this term now. So 2 times the 2 newtons times the 3 meters that our block slides. Let's go calculate that now. What is our new velocity? We got 6.79 meters per second instead. As expected, because we had work done on our system by an external force, more energy was put into our system. And in this case, the energy went into kinetic energy, and so we had a larger speed.